Imagine this. Every time you fill your car, you aren't just fueling an engine, you're tapping into a time vault of life from hundreds of millions of years ago. What if I told you that crude oil isn't just ancient chemistry, it's a library of DNA fragments from prehistoric marine ecosystems? How could DNA survive deep underground at temperatures from 60 to 180 degrees Celsius for millions of years? And what secrets could these molecular fossils, not bones, not shells, unlock about Earth's deep history? Imagine if oil is not just the fuel for our cars, but also a storage of ancient life, preserving genetic material from organisms that lived millions of years ago. Are we really burning dinosaurs? Recent research suggests that crude oil contains fragments of DNA that could rewrite our understanding of Earth's history. Scientists uncovered over 3 million DNA fragments embedded in petroleum, which reveals about ancient ecosystems. They sequenced millions of these fragments. Most turned out to be from environmental DNA, genetic material from microbes, algae, and other organisms that had lived in the vicinity over time. A smaller fraction was ancient DNA, DNA left behind by long-dead species from geological epochs past. Why is DNA in oil such a big deal? Well, oil forms deep underground under heat, usually 60 to 180 degrees Celsius, and pressure over millions of years. A tough environment where you'd expect almost all DNA to degrade. Yet, these researchers showed that some DNA manages to survive, especially environmental fragments from microbes or algae that lived nearby after deposition, or long before. Remarkably, some fragments appeared to date back to ancient life, essentially transforming petroleum into a new kind of fossil. Not bones or shells, but molecular fossils of DNA trapped deep in oil. Let's break it down. Scientists categorized sequences into 3 types. Ori-DNA, the original in situ DNA from organisms that became oil. Very little of this survived. Pre-DNA, relatively recent environmental DNA, say from bacteria or human-associated microbes, things that seeped into reservoirs in more recent times. Pay-DNA, truly ancient DNA, from long-gone species, offering evolutionary insights. Most of the DNA they pulled out turned out to be pre-DNA, like microbial contamination over time. But crucially, they also identified pay-DNA sequences that appeared to come from organisms that were alive as far back as the Paleocene epoch and even earlier. They found signals pointing to ancient marine incursions, when sea levels rose and flooded the basin, ancestral bird species, potentially unclassified early hominids, and even creatures like kiwi birds and ancient yaks that are not native to China today. Scientists used something called the mega-screening method, a rigorous filtering process to sort environmentally derived DNA from ancient DNA. Essentially, they compared each fragment against massive DNA databases, searching for matches and patterns that indicate ancient origins. They also paid attention to things like fragment length and similarity scores to separate contamination from genuine ancient signals. Interestingly, many of the ancient fragments didn't show a key hallmark of old DNA called deamination, a chemical change that DNA undergoes over time. This contradicts the common assumption that ancient DNA always exhibits that damaged signature. So why does this matter? First, it opens a completely new window into ancient life, especially places where physical fossils are rare. Oil reservoirs now become archives of molecular history. Second, in geology, petroleum has always told us about ancient environments through chemical biomarkers, molecules like hopanes and steranes that come from algae or bacteria. But now we have actual genetic fragments, a direct link to the organisms themselves, not just their chemical signatures. And third, it invites us to integrate disciplines, genomics, paleontology, geology, even archaeology. Oil fields become surprise time capsules recording ancient ecosystems, migrations, climate changes, and possibly even early human or bird presence in regions. However, There are critical methodological concerns about distinguishing contamination from real ancient DNA, especially because oil passes through layers that can mix modern and older DNA fragments. They advocate improving screening protocols, expanding DNA reference databases, and being cautious in attributing fragments to ancient species without stringent evidence. Despite that, the door is now officially open. Let's zoom out from DNA and oil and ask, where do fossil fuels come from, globally speaking? Which countries and regions hold the biggest coal, oil, and gas reserves, and why? Coal is the most widespread fossil fuel. Coal reserves are found on every continent, but the largest stocks of proven coal are concentrated in 5 countries: the United States, approximately 22% of global reserves; Russia, approximately 15%; Australia, approximately 14%; China, approximately 13%; and India, approximately 10%. Geologically, these areas were swampy and forested during the Carboniferous and Permian periods, making them ideal for the accumulation and preservation of plants over millions of years. Oil is highly concentrated in a few regions. Nearly 48% of the world's proven oil reserves are located in the Middle East, particularly around the Persian Gulf, with giants like Saudi Arabia's Ghawar field being among the largest in the world. Other key oil-rich regions include Western Siberia and the Volga-Urals Basin in Russia, the Permian Basin in the US and the Alberta oil sands in Canada, Venezuela's Orinoco Belt, offshore Brazil, and the Niger Delta in Africa. In terms of recent output, the United States, Russia, and Saudi Arabia led global oil production, accounting for roughly 9 to 12% each of the daily global oil output. Natural gas reserves tend to co-occur with oil, but they are more evenly distributed. The top 5 gas reserve holders are Russia, 24%, Iran, 17%, Qatar, 13%, Turkmenistan, 10%, and the United States, 6%. U.S. shale gas, including the Marcellus, Barnett, and Eagle Ford basins, has driven a significant surge in American gas production over the past decade. So there you have it. Fossil fuels were born millions of years ago in specific geological settings: coal from ancient forests, oil and gas from buried marine life in sedimentary basins. And today, they're primarily extracted from just a handful of countries hosting both reserves and infrastructure capable of turning them into the energy we use. So, are we really burning dinosaurs? No, we're not burning dinosaurs. Here's why that idea is a myth, and what fossil fuels actually come from. The notion that oil, gas, and coal are formed from the remains of dinosaurs is widespread, but scientists say it's incorrect. Sinclair Oil, in the 1930s, used a dinosaur mascot to imply a direct connection between dinosaurs and petroleum, which stuck in the public imagination. Oil and natural gas. These come from microscopic marine organisms, such as algae, plankton, and bacteria, that lived and died millions of years before and during the time of the dinosaurs. These organisms washed to the seafloor, were rapidly buried in oxygen-poor sediments, and were gradually transformed by heat and pressure into oil and gas over hundreds of millions of years. Coal is formed almost exclusively from terrestrial plant matter, such as trees and ferns, buried in ancient swampy environments, primarily during the Carboniferous period, approximately 300 million years ago, well before the existence of dinosaurs, approximately 230 to 65 million years ago. Dinosaurs did not make fossil fuels for several reasons. Too few and too scattered. Dinosaurs were rare compared to the vast biomass of algae and plankton. Their bodies weren't abundant enough to form significant fuel deposits. Poor burial conditions. Dinosaur carcasses tend to decompose quickly and attract scavengers, which prevents the rapid, oxygen-free burial necessary to form fossil fuels. The discovery of molecular DNA fossils deep within petroleum reminds us that every barrel of oil is ancient life. When we burn fossil fuels, we aren't simply combusting dead biomass, but we're releasing carbon that was locked away over geological epochs, carbon that Earth's systems captured and stored for long-term balance. Burning these stored carbon reserves today drives rapid climate change, which raises serious ethical concerns. Tap the like button, subscribe, and ring the bell so you don't miss our next story. Do you have questions or a story you'd like to cover in the next videos? Drop them in the comments. We love hearing your ideas. Until next time, stay curious and keep uncovering the hidden stories of our planet journey.